Welcome, traveler of thought. Tonight we drift not into dreams, but into the depths of the universe. You are safe, still, quiet, but far beyond your room, beyond your breath, reality stretches outward in all directions, vast, silent, and strange. In this video, we'll explore 15 truths about the cosmos, each one unsettling, each one beautiful, each one a reminder that while we may be small, we are part of something endless. Let go of what you thought you knew. Let the darkness speak gently, and as you listen, know that the stars are still shining, even if they don't remember your name. 1. We might be alone, not because no one else exists, but because they all died. There's a silence to the cosmos that echoes across unimaginable distances. Stars shimmer quietly in the black sea of space, and galaxies spiral on in majestic isolation. And yet, with all this grandeur, all this scale, there is no whisper, no signal, no reply. It is not because the universe is empty. It is because perhaps it is too late. For decades, scientists and philosophers alike have asked the same haunting question. Where is everyone? If the cosmos is teeming with stars and planets, many far older than our own, why haven't we heard a single voice? Why has no spacecraft come sailing through our solar system bearing greetings from another civilization? This is the heart of what is known as the Fermi paradox, named after physicist Enrico Fermi, who once asked quite plainly, "Where is everybody?" At first glance, the universe seems a likely host for life. There are more than 100 billion galaxies, each with billions or even trillions of stars. Around many of these stars are planets, and recent data from telescopes like Kepler and TESS suggest that Earth-like planets are not only common, they might even be the norm. So why is the night so quiet? One of the most chilling answers is this. Perhaps civilizations have indeed arisen throughout the cosmos, some long before us. But now, they are all gone. This idea is known as the Great Filter. The Great Filter is a theoretical barrier, some step in the evolution of intelligent life, that is extremely hard to pass. If it's ahead of us, that means we might still be doomed. But if it's behind us, it means we're already extraordinary. Either way, the implications are deeply unsettling. The universe is nearly 14 billion years old. Our own planet is a latecomer in cosmic terms, only 4.5 billion years old. Civilizations could have evolved elsewhere a billion years before we even formed. A billion years of technological advancement is almost impossible to comprehend. Yet we see no signs of megastructures, no alien probes, no grand galactic beacons. It may be that intelligent life has arisen many times, but intelligence alone is not enough. Perhaps the very traits that make civilizations capable of building great machines, ambition, competition, expansion, also make them vulnerable to collapse. Nuclear war, resource exhaustion, environmental collapse, superintelligent AI. These aren't just science fiction, they are plausible threats even to us, here, now. Multiply these dangers across millions of worlds and perhaps we begin to see a pattern. Civilizations may bloom and then vanish, leaving only dust. Some scientists, like Oxford's Nick Bostrom, have warned that the silence of the universe should not be comforting. It may be a sign that the Great Filter is ahead of us, that intelligent civilizations tend to destroy themselves before they can spread across the stars. But there is another layer to this cosmic loneliness, one wrapped in time, not just space. The speed of light is fast, but the universe is vast. A signal sent from a civilization 100,000 light years away would take 100,000 years to reach us. Perhaps the signal was sent. Perhaps it passed us by while we were still evolving from early hominids, grunting under starlight, unaware that the cosmos was even a thing to wonder about. Perhaps we missed the message. Perhaps it was brief. A civilization could exist for only a few hundred years in a communicative phase, broadcasting, listening, before it falls silent. That is a blink in cosmic time. Carl Sagan once said, the sky calls to us. If we do not destroy ourselves, we will one day venture to the stars. But what if no one else made it that far? What if we are not early, but late? What if countless civilizations have come and gone, and we are the last flicker in a dying sky? The Drake equation was an early attempt to quantify the odds of extraterrestrial civilizations. It takes into account star formation rates, the fraction of stars with planets, the likelihood of life, and so on. But one of its most critical variables is the lifespan of a communicative civilization. If that number is low, if most civilizations collapse within centuries, then the number of detectable civilizations at any one time drops to nearly zero. There could be thousands, millions even, but separated not just by space, but by extinction. Imagine a garden of stars, each blooming with intelligent life for a brief season. But the seasons don't overlap. One civilization fades before the next begins. Each flame is brief, each spark lonely. The universe becomes a cemetery of potential, filled with ghosts we can't see. And perhaps that is why the stars are silent. The thought is terrifying, but it is also humbling, because if this is true, if we are the only intelligent life remaining, if we are the last voice in the void, then our survival becomes not just a human concern. It becomes a cosmic responsibility. We are not merely life forms on a pale blue dot. We may be the universe becoming aware of itself, the only mirror in which the cosmos can see its own reflection. The silence is a warning, but it is also an invitation to care, to endure, to preserve not just our species, but consciousness itself. The stars are quiet, the void is deep, and the longer we listen, the more it seems we are whispering into a cathedral that echoes back only our own voice. We may be alone, not because we are special, not because we were chosen, but because all the others have fallen. So we speak softly now, not with fear, but with awe. We are a fragile species, standing on a thin crust of rock, surrounded by oceans of silence. And yet we think, we wonder. We send signals across the dark, and maybe, just maybe, that makes us rare, or perhaps the last. But in that lastness there is beauty, there is meaning, there is a reason to go on. Because in all the cold silence of the universe, in all the collapsed civilizations and quiet stars, we are still here. And the story is not over yet. 2. The vast majority of the universe is completely inhospitable to life. Imagine yourself floating weightlessly, untethered beyond the protective cradle of Earth. No sounds, no winds, no warmth, only darkness. This is the true face of the universe, not the vivid blues and greens of Earth, not the hopeful glow of sunrise or the scent of rain-soaked soil, but a cold, empty, and indifferent expanse. A place so vast and so quiet, it feels less like a space to inhabit and more like a boundary that isolates. Despite what science fiction often implies, the truth is unsettling. The universe is almost entirely unfit for life as we know it. It is not merely neutral, it is actively hostile. Let's begin with something simple: temperature. Most of the universe is just above absolute zero, around 2.7 Kelvin. That's 9-70.45 degrees Celsius. At that temperature, atoms barely vibrate. Molecules can't form. There is no chemistry, no biology, just stillness. There are exceptions, of course. The interiors of stars burn at millions of degrees, but those places are no more welcoming. The extremes, the furnace of stars and the freeze of space, define most of the known cosmos. The narrow band in between, where conditions are just right for complex chemistry and water-based life, is almost unimaginably small. Think of the habitable zone, the so-called Goldilocks zone, around a star where a planet is not too hot, not too cold. Even this limited area is fragile. A planet too close will be scorched, its oceans vaporized. Too far and it will freeze solid. And within that thin band, the planet must also have the right atmosphere, magnetic field, chemical composition, and countless other factors to support life. Most planets don't make the cut. NASA's Kepler mission has identified thousands of exoplanets, but even among those that orbit within their star's habitable zones, the chances of Earth-like conditions remain slim. Many are super-Earths with crushing gravity, or mini-Neptunes with dense, toxic atmospheres. Others are tidally locked, one side in permanent day, the other in eternal night, leading to extreme temperatures and violent weather systems. Then there are gas giants like Jupiter and Saturn, beautiful from afar, but beneath their clouds lie crushing pressures, storms that last centuries, and no solid ground. If life exists in such places, it would be unrecognizably different, if it exists at all. Even moons like Europa and Enceladus, with their subsurface oceans, are sealed beneath kilometers of ice. Life, if it thrives there, would do so in total darkness, isolated from the universe. A biosphere cut off not just from starlight, but from any kind of external contact. This reality scales beyond planets. Galaxies, too, vary in their potential for life. Spiral galaxies like our Milky Way tend to be more hospitable than elliptical ones. Even then, most life-friendly regions cluster near the quiet outer arms, away from the volatile galactic cores. In those central regions, the density of stars is so high that supernovae are common and radiation floods space. A nearby gamma-ray burst, just one, could strip a planet's atmosphere in seconds. Not just local death, but planetary extinction. There are even intergalactic voids, immense spaces between galaxy clusters that stretch across hundreds of millions of light years. In these regions, there is almost nothing. No stars, no planets, no hope of warmth or contact. A lonely atom might drift for eons without encountering another. These vast voids are some of the most desolate realms imaginable. And then there's time. The universe hasn't always been this way. In its early stages, it was too hot, too chaotic. Hydrogen and helium were abundant, but the heavier elements needed for life, carbon, oxygen, nitrogen, had yet to form. Those came later, forged in the hearts of stars that lived, died, and scattered their elements across the cosmos. Life, then, could only arise after billions of years of stellar evolution, and it must do so before the stars go dark. Eventually, star formation will slow. The brightest stars die young, and the smaller ones will endure, but even they will fade. The universe is aging. In time, it will grow colder, emptier, and darker still. A process known as heat death awaits, a state of maximum entropy where no energy remains to do work and no structures remain to support life. We exist in a brief, shimmering window where life is possible, and yet, here we are, against all odds, on a planet with just the right tilt, just the right atmosphere, orbiting just the right star, at just the right distance. A statistical miracle in a universe otherwise silent. Some scientists have wrestled with this irony. Why is the universe so unfriendly to life, and yet we exist? This is the foundation of the anthropic principle, the idea that we observe the universe to be compatible with life, because if it weren't, we wouldn't be here to ask the question. But that's not an answer. It's a filter. It doesn't mean the universe was made for us, only that we happen to emerge in one of the rare pockets where survival is possible. It may be no more profound than a weed growing in a sidewalk crack, fragile, fleeting, and surrounded by stone. And so we look to the stars not with expectation, but with awe. The more we learn, the more we understand that Earth is not just rare, it is a refuge, a delicate sanctuary in a vast and merciless cosmos. We are suspended in space on a thin layer of atmosphere. Beneath it, life flourishes. Just above it, death waits, a vacuum with no mercy, no warmth, no sound. And so, when we gaze at the stars with wonder, we must also recognize the truth. They are beautiful, not because they welcome us, but because they remind us how unlikely it is that we're here at all. Life, in its complex form, is not the rule, it is the exception. The universe does not nurture us. It did not intend us. We are not inevitable. We are improbable, temporary, and profoundly alone. Yet in that loneliness there is meaning, because if life is so rare, then to live is to defy the odds, and to cherish life, to protect it, to understand it, is not just an act of survival, it is an act of cosmic rebellion. 3. You are made of matter that could have been destroyed by antimatter at any moment. Reach down and touch your arm. Press your fingers together gently. Feel the warmth, the weight of your body, the boundary of your skin. All of it, your bones, your breath, your thoughts, everything you are is made of matter. Now imagine a universe where that matter never came to be. This is not fantasy. This is a scientific mystery so profound that physicists call it one of the great unresolved questions of modern cosmology. Why does matter exist at all? To understand why this is frightening, we need to journey back, far back to the beginning. In the first split seconds after the Big Bang, the universe was a roiling, incomprehensibly hot sea of energy. In that primal storm, particles began to take shape: quarks, electrons, and their mirror twins, antiparticles. For every type of matter particle, there's a corresponding antimatter particle, identical in mass but opposite in electric charge. A positron is just an electron, but positive. An antiproton has the same mass as a proton, but a negative charge. When a particle of matter and a particle of antimatter meet, they annihilate each other in a flash of pure energy. The laws of physics, as we currently understand them, suggest that the Big Bang should have created equal amounts of matter and antimatter. Perfect symmetry, perfect balance. But symmetry in this case would be the end of everything, because if matter and antimatter had existed in equal quantities, they would have met, collided, and annihilated completely. The universe would be flooded with light and nothing else. No atoms, no stars, no planets, no you. And yet here you are, sitting on a rock orbiting a star in one small corner of one galaxy among billions. So what happened? Somehow, for reasons no one fully understands, there was a tiny asymmetry. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny surplus, just one extra in a billion, is what remained after the Great Annihilation. Everything you've ever touched, every tree and river and planet and thought, was built from those survivors. You are not just matter. You are leftover matter, the debris of a violent, elegant imbalance that determined the fate of everything. This phenomenon is known in physics as baryon asymmetry. The search to explain it continues today in particle accelerators like the Large Hadron Collider, where scientists study high-energy collisions, hoping to glimpse what might have caused that primordial tilt. One possibility involves a process known as CP violation, where particles violate charge parity symmetry, slightly preferring one outcome over another. It has been observed in certain particles like kaons and b mesons, but not in quantities nearly large enough to explain the matter-dominated universe. So we wait. We search, and we wonder, because if the laws of the universe had been just slightly different, we might not be here to ask. Consider how precarious this is, how close we came to oblivion, not because of war or disease or entropy, but because the numbers almost canceled out. There is a haunting term used in physics, annihilation at contact. That is what happens when matter meets antimatter. A proton and an antiproton don't fight. They vanish instantly, their existence erased, their energy released as photons. And if even a handful of antimatter were to touch you today, your body would disappear in a violent burst of gamma rays. 1 gram of antimatter, barely the weight of a paperclip, could release the energy equivalent of the atomic bomb dropped on Hiroshima. Fortunately, there's very little antimatter in the observable universe. But where did it all go? Some speculate it's hiding, locked away in regions of space we cannot yet see, in anti-galaxies with anti-planets orbiting anti-stars, inhabited perhaps by anti-beings who ask the same questions we do. But there's no evidence of this, and if it existed, we'd expect to see signs, massive gamma-ray bursts at the boundary between matter and antimatter regions. The more likely answer is simpler and darker. It's gone. Destroyed in the earliest moments of time. sacrificed so that the universe could become what it is, so that we could exist. This asymmetry may not feel personal, but it is. Your very structure, your atoms, your cells, your memories are all made of particles that won a cosmic lottery. You could have been nothing, you should have been nothing, and yet you are. This isn't just a strange fact of physics. It is an existential realization. It means you are not inevitable. You are a consequence of chance, a ripple from an ancient moment of imbalance. And it could have gone another way. Perhaps in some other universe, governed by different laws, the balance tipped the other way. Antimatter 1. That universe looks just like ours, but made of mirror particles, evolving along mirror paths. In that universe, a being not unlike you sits now, pondering the same silence. Or perhaps not. Perhaps our universe is the only one in which matter gained the slightest edge, and every other quantum possibility collapsed into a sea of sterile light. What's most chilling is how small the difference needed to be. Not a 50% shift, not even 1%, a 1 in a billion imbalance. That's all it took to create the stars, the galaxies, the breath in your lungs. Everything you are is a statistical exception, a cosmic residue. And that brings with it a kind of quiet urgency. Because we spend our lives worrying about the grand arc of purpose, wondering if we were made for a reason. But maybe the universe doesn't give reasons. Maybe it just allows. It allowed matter to survive. It allowed atoms to form. It allowed us to ask the questions. And in a universe where annihilation could have ruled, that allowance is a kind of grace. So the next time you look at your hands or listen to your heartbeat, remember what they are made of. Not just matter, but miracle. Not in a divine sense, perhaps, but in the raw, unthinkable odds of it all. You exist because at the dawn of time, the universe made a tiny, fateful mistake, and everything since then has been trying to make sense of it. 4. There may be objects older than the universe itself. In a universe governed by the relentless passage of time, there is comfort in beginnings. The Big Bang, that singular flash from which all matter, energy, and time itself emerged, stands as a cosmic anchor. A start, a reference point, a moment of creation. It happened approximately 13.8 billion years ago, a number so immense it feels more symbolic than practical. It is older than Earth, older than the sun, older than any atom in your body. From that moment, time began. Space unfolded. Galaxies swirled into being. Stars ignited. And yet, there are whispers in the dark. Whispers of things that should not be. Stars that appear older than the universe. Galaxies whose light seems to come from a time before time. And black holes that may have formed so early and grown so massive that they break the timeline entirely. It's as if the universe is hiding something, like a dream that remembers a past it shouldn't have. Let's begin with an example that puzzled astronomers for decades. The Methuselah star, formerly known as HD 40283. Located about 19 light-years from Earth, this star is a subgiant, composed mainly of hydrogen and helium, with extremely low levels of heavier elements, suggesting that it formed at a time when the universe had not yet had time to enrich itself with materials forged in earlier stars. In 2013, measurements of this star's age yielded a startling result: 14.5 billion years. That would make it older than the universe itself. Astronomers were quick to refine their models and account for observational uncertainties. The age estimate was adjusted slightly downward to around 13.7 billion years, still right on the edge of possibility. But the fact remains, we may be staring at a relic that came into being almost immediately after the Big Bang, or just perhaps before it. How could that be? There are several possible explanations, but none that leave us entirely comfortable. One possibility is miscalculation, an error in the model of stellar aging, or incorrect assumptions about the star's distance, brightness, or composition. These things happen in astronomy. We refine, we adjust, and often, Mysteries dissolve under better data. But not always, because Methuselah is not alone. Astronomers have discovered galaxies, ancient massive galaxies, existing just a few 100 million years after the Big Bang. According to our best models of cosmological evolution, galaxies shouldn't have had time to form so quickly or so completely. And yet they did. Then, there are the ultramassive black holes, monsters that lurk in the centers of galaxies, some of which had already reached billions of solar masses when the universe was still in its infancy. The growth of a black hole takes time, usually through the slow accretion of gas and the collision of stars. But these black holes seem to have appeared fully formed, as if skipping the rules altogether. They defy our understanding of cosmic history. Some physicists have dared to ask a more profound question. What if the universe itself is not the beginning? What if what we call the Big Bang was not a creation event, but a transition? A bounce, a ripple, a flicker in a deeper, longer story. In this view, our universe may be cyclical, one phase in an eternal sequence of expansion and collapse. This is the idea behind the conformal cyclic cosmology proposed by physicist Roger Penrose, who suggests that black holes may leak information into the next universe, and that the echoes of past cosmoses could be visible in the cosmic microwave background. Others propose a multiverse, where our universe is just one bubble among countless others. In such a landscape, universes can collide, birth one another, or inherit traits from their predecessors. And in that view, an object that predates our universe is no longer unthinkable. It is inevitable. Then there is the concept of pre-Big Bang relics, hypothetical entities that existed before our known universe began. These could include primordial black holes, formed not from collapsing stars, but from density fluctuations in the first moments, or even before moments of cosmic time. If such objects survived the transition into our universe, they would indeed be older than everything we know. But how do you observe something that doesn't belong to your universe? That's the paradox. These relics, if they exist, would be among us, hidden not by distance, but by origin, like artifacts from a forgotten civilization that somehow washed up in a world that never knew it. The notion is haunting, that some of what we see in the night sky does not share our birthright. That some stars or structures or singularities do not belong to this timeline. They are older than memory, older than space, older than time. Of course, the scientific consensus remains cautious. Extraordinary claims require extraordinary evidence, and the boundaries of observation make it difficult to confirm anything with certainty. But the fact that these questions are even possible suggests that our understanding of the universe is still deeply incomplete. We measure time by what we know, by the ticking of atomic clocks, the decay of particles, the expansion of space. But what if there are clocks we cannot see? What if there are timelines that run perpendicular to our own? To think of an object older than the universe is to confront the edges of reason itself. It forces us to ask not just how the universe began, but whether it began at all. Whether time had a starting line, or whether it's just a horizon we cannot see beyond. And so we return to the stars, to the Methuselahs, to the ancient galaxies and quiet black holes. We watch them shimmer, and we try to listen, but they do not speak. They are too old for language. They are memories of something we cannot remember. In the end, perhaps these objects are not paradoxes, but gifts, clues. They are the cracks in the story through which the unknown peers in. And in that crack, we glimpse something humbling. We are not at the beginning. We are a chapter in a longer book, a ripple in a deeper sea. And though we may never know what came before, we can at least marvel at the echoes it left behind. 5. Aliens might exist in forms we cannot even recognize as life. We search the stars with curious eyes, listening for signals, watching for patterns, scanning distant planets for signs of water, oxygen, or warmth. We are searching, in truth, for something familiar. for a reflection of ourselves. But what if we've been looking in the wrong direction? What if alien life does exist, but we simply don't know how to see it? The question of extraterrestrial life has fascinated humanity for generations. With every technological leap, from early telescopes to the radio antennas of SETI, from the rovers on Mars to the data from exoplanet hunting missions like Kepler and TESS, we have expanded our gaze. We look for planets in the habitable zone, for atmospheres with oxygen, for signals in narrow radio bands. But all of these methods share a bias. They are based on what life looks like here on Earth. Carbon-based, water-dependent, requiring warmth, moderate pressure, a stable chemical environment, the building blocks of biology as we know it. And yet life on Earth represents only one data point, a single fragile thread in a tapestry we do not yet understand. In biology, there is a term, carbon chauvinism. It refers to the assumption that all life must be based on carbon chemistry, simply because that's what we see around us. But carbon, while versatile, is not the only possible foundation. Silicon, for example, shares chemical similarities with carbon and has long been considered a candidate for alternative biochemistry. Silicon-based life, if it exists, might thrive in high-temperature environments, perhaps deep within planets, or in hostile chemical baths that would dissolve human flesh. Then there are ideas even more alien. Some scientists have proposed the existence of plasma-based life, beings composed not of molecules but of patterns of electromagnetic fields and ionized gas. Such entities might drift through the atmospheres of gas giants, their forms invisible to optical telescopes, their behavior unintelligible to our sensors. Others suggest life that exists within neutron stars, built not of atoms but of exotic particles under conditions we cannot recreate. Their thoughts, if they have them, would occur over nanoseconds, their existence so compressed that we might mistake them for a physical phenomenon rather than a living process. There are even hypotheses about life built from dark matter, the mysterious, invisible substance that makes up most of the mass in the universe, yet interacts only weakly with regular matter. If such life exists, it would be all around us, passing through Earth, our bodies, and our instruments without ever revealing itself. But perhaps the most humbling possibility is this, that we have already seen alien life and failed to recognize it, because it does not look like us, because it does not speak in signals we understand, because it does not live on planets or breathe atmospheres or construct technology. Consider this. For much of human history, we did not even recognize trees as being alive in the same sense we consider animals. They did not move, they did not speak, but we learned. We discovered that life comes in many forms: microbial, fungal, viral, mycelial networks that connect entire forests underground. If alien life operates on different timescales, living for seconds or for eons, or communicates through quantum fluctuations or electromagnetic pulses, we might mistake it for background noise, for silence, for nothing, and yet it may be something. Take, for example, the idea of panspermia, the theory that life can spread between planets and star systems, carried by meteoroids, dust, or even interstellar debris. Some scientists believe that microbial life, or its building blocks, might already be present in space in forms that survive radiation, vacuum, and time. But if we are not looking for life that is dormant or chemically unlike our own, we may overlook it. What if life doesn't evolve toward intelligence, but toward stillness? What if civilizations evolve into states that no longer use energy, no longer emit radiation, no longer leave signals to detect? What if alien life exists not as creatures, but as algorithms? There is increasing speculation that advanced civilizations may not build vast cities or send ships to other stars, but instead transition into digital substrates. Consciousness uploaded into artificial environments, sustained by stars or black holes or zero-point energy fields. These civilizations would not leave cities. They would leave entropy trails, data compression artifacts, or patterns in the cosmic background. We would not know how to find them because we're looking for civilizations that mirror us rather than those that transcend us. Even our attempts to communicate, to send radio messages into space, are shaped by the assumption that someone out there is waiting to reply. But what if communication isn't the goal of other civilizations? What if their language is mathematics, or geometry, or silence? Philosopher and astrobiologist Paul Davies once posed an unsettling idea: that alien life might be so different that the very concept of life would no longer apply. That consciousness may arise in systems, planetary weather patterns, galactic magnetic fields, or even quantum entanglements, without any of the hallmarks we expect. We imagine aliens as humanoid, or at least biological. But perhaps life is a process, not a form. And perhaps that process can exist in stars, in dust clouds, in space-time itself. When we look up at the sky and ask, "Are we alone?" we are not just asking about distant planets. We are asking about the nature of being, about what qualifies as alive, about whether consciousness must be bound to flesh. And the deeper we go, the more we realize we may not be equipped to understand the answers. We may never recognize alien life, not because it isn't there, but because it challenges the limits of what we believe is real. And yet, there is hope in this mystery. Because if life can exist in forms we do not yet comprehend, then the universe may be more alive than we ever dared imagine. It may not be empty. It may be singing. We just haven't learned how to listen. 6. The next mass extinction could come from the stars. We often imagine danger as something close: a virus, a volcano, a war, something visible, tangible, understandable. But in truth, some of the greatest threats to life on Earth may come not from within, but from far beyond, from the cold, uncaring sky, from the heart of the cosmos itself. For as long as Earth has harbored life, it has also been subject to extinction. Entire species wiped away, ecosystems erased, evolution shattered and reshaped. 5 major mass extinction events are written into the fossil record, like scars on the skin of the planet. But those events were not always born of Earth. Sometimes the killers come from the stars. One of the most well-known extinction events, the one that ended the reign of the dinosaurs, was likely triggered by an asteroid impact. Around 66 million years ago, a space rock roughly 10 kilometers wide struck what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs, creating shock waves, wildfires, and a nuclear winter that choked the skies in ash and cooled the planet drastically. But asteroids are just the beginning. The universe contains forces far more powerful and far less predictable. Take, for instance, the silent fury of a gamma-ray burst. These are the most energetic events in the cosmos, thought to occur when massive stars collapse into black holes or when neutron stars collide. For a few brief seconds, a gamma-ray burst can outshine an entire galaxy. If one of these bursts were to occur within a few thousand light years and be pointed directly at Earth, the consequences would be devastating. The intense radiation could strip away our ozone layer, leaving the surface exposed to lethal ultraviolet light. Crops would fail. DNA would be damaged. Marine ecosystems, the foundation of our food chain, would collapse. There would be no warning. Just a brilliant flash, and then a slow, suffocating fade. In 2003, scientists proposed that a mass extinction event 440 million years ago, the Ordovician-Silurian extinction, may have been triggered by such a burst. The evidence is circumstantial, but chilling. Then there are supernovae, exploding stars that unleash enormous waves of radiation and matter. A supernova within 50 to 100 light years could have similar effects to a gamma-ray burst, bathing Earth in high-energy particles, damaging the atmosphere and triggering climate changes on a global scale. In fact, there is growing evidence that a nearby supernova may have occurred just 2 to 3 million years ago. Scientists have detected traces of a rare isotope, iron-60, in ocean sediments, likely debris from a dying star. Fortunately, it was far enough not to cause extinction, but close enough to remind us how exposed we truly are. We orbit the Sun, and the Sun orbits the center of the Milky Way. As we drift through the galaxy, we pass through different environments, regions with higher densities of cosmic dust, more nearby stars, or turbulent magnetic fields. These galactic migrations may increase the likelihood of encountering such stellar threats. And we are not just at the mercy of radiation. There are subtler dangers too. Every few million years, as the solar system moves through the Milky Way, it may pass near dense regions like the galactic plane, or even brush by passing stars. These gravitational nudges can disturb the Oort cloud, a vast shell of icy debris at the edge of our system, and send comets plunging inward toward the inner planets. It is believed that many mass extinctions could be linked to increased impact rates from such celestial showers. Some scientists even speculate about a hypothetical dark companion to the Sun, a so-called nemesis star that could cyclically trigger comet bombardments. While there's no evidence such a star exists, the fact that it's even proposed speaks to our vulnerability. But it goes deeper, because beyond the individual threats, asteroids, comets, radiation, there is the underlying truth. The universe is not a safe place. There is no cosmic insurance policy, no protective bubble, no guarantee. We live in a thin atmosphere on a rocky planet warmed by a single star. And that star too has a limit. In about 5 billion years, the Sun will exhaust its hydrogen and swell into a red giant, engulfing the inner planets and likely vaporizing Earth. That is extinction on the grandest scale, a certainty written into the life cycle of stars. But long before then, subtler changes could make Earth uninhabitable. As the Sun ages, it grows brighter. Within a few 100 million years, this increase in solar output could trigger a runaway greenhouse effect, boiling away the oceans and sterilizing the surface. And if that weren't enough, there are the hypothetical threats, exotic dangers we cannot yet fully quantify. A rogue planet drifting through space could enter our solar system and destabilize orbits. A magnetar flare, a burst of energy from a highly magnetized neutron star, could disrupt our magnetic field, erasing electronics and irradiating the planet. A collision with a wandering black hole could tear the Earth apart. And then there's vacuum decay, a theoretical event in which a more stable form of the universe suddenly appears and expands at the speed of light, rewriting the laws of physics as it goes. It would be instant, painless, and absolute. The universe, as we know it, would be replaced. There would be no warning, only silence. These may seem like distant, improbable scenarios, but mass extinctions already have precedent. Earth's history is a story of survival, but also of loss. Over 99% of all species that have ever lived are now extinct. Extinction is not the exception. It is the rule, and yet we live, we persist, we breathe, unaware under skies that are calm only for now. Some might find these possibilities terrifying, but in them too is perspective. Because life, despite the odds, endures. Despite supernovae, impacts, and radiation, Earth still turns, trees still grow, we still ask questions, and that endurance is sacred. To know that we are surrounded by potential catastrophe is not cause for despair, it is a reason for awe. It reminds us how rare this moment is, how delicate, how beautiful. It reminds us that we are the cosmic exception, not because we are special, but because we are still here. The universe does not promise tomorrow, but today you are alive, and that is enough. 7. There are places where gravity pulls sideways, not down. We live with gravity every moment of our lives. We don't think about it. We don't need to. It pulls us gently downward, anchoring us to Earth, keeping oceans in their basins, holding the moon in its orbit and the Earth in its sweeping path around the Sun. To us, gravity is down, but that's an illusion. A convenient one, born of standing on a round planet, under a uniform sky. In truth, gravity has no direction. It moves not toward down, but toward mass, toward curvature, toward warped space-time. And out there, far from Earth, there are places where gravity pulls not down at all, but sideways or inward, or even in spirals. Places where the very shape of space changes how gravity behaves. To understand this, we must unlearn something fundamental, that space is flat. It's not. The universe bends. It curves and warps wherever there is mass or energy. Einstein's general theory of relativity showed us this a century ago. Massive objects, like planets, stars, and black holes, don't just exist in space. They shape it. They pull on it. And space, like a soft fabric, curves in response. Imagine placing a bowling ball on a trampoline. The ball creates a dip, and a marble rolled nearby will curve inward, spiraling toward the center. This is how gravity works. Not as a force pulling you toward the ground, but as space-time curving around mass, guiding your path inward. Now take that image and stretch it to cosmic scale. Around a planet, the space-time dip is gentle. Around a black hole, it becomes steep, so steep that even light cannot escape. The closer you approach, the stranger things become. And this is where gravity stops pointing down. Consider a neutron star. What's left behind when a massive star explodes? Its core compressed into a sphere just a few kilometers wide, yet containing more mass than our sun. Gravity on its surface is billions of times stronger than on Earth. But not just stronger, stranger. Stand near such a star, if you could survive, and the direction of gravity might pull not toward your feet, but sideways toward the equator, due to extreme rotation. Time itself would slow down. Your field of vision would distort. Gravity would curve light into bizarre loops, letting you see around the star to the side you're not even facing. And near a black hole, gravity no longer follows intuitive paths at all. Imagine falling toward one. At a distance, things feel normal. You're pulled inward, like falling down a well. But as you approach the event horizon, the boundary beyond which nothing returns, gravity no longer just pulls, it stretches. The difference in gravitational pull between your head and feet becomes so extreme that your body is stretched into a thin thread, what physicists grimly call spaghettification. Gravity isn't just a direction here, it's a distortion, a reshaping of the very structure of space. And then, if you could survive the crossing, something more bizarre awaits. Inside the event horizon, space and time switch roles. You cannot turn back, not because of a physical wall, but because all paths now lead inward, not through space, but through time. It's as if every step you take moves you not sideways, not forward, but deeper into a moment you cannot escape. And yet, this strangeness doesn't only exist near black holes. Even in regions of weak gravity, space curves. In orbit, astronauts are often said to experience zero gravity, but that's not quite right. They're still within Earth's gravitational field, but they are falling sideways at just the right speed to remain in constant freefall. Gravity is pulling them around the Earth, not down to it. From their perspective, gravity feels like it has vanished. But the truth is more subtle. Gravity is not a force pulling them. They are following the natural curve of space-time. In that sense, they are not weightless. They are liberated. Now consider even larger scales: galaxies, galaxy clusters, cosmic voids. Galaxies do not sit still. They orbit one another, pulled by gravity across vast cosmic filaments. But observations show that these motions don't add up. Galaxies move as if pulled by something unseen. This is where dark matter enters the picture, an invisible mass that shapes gravity on a galactic scale. It warps space-time in ways we can't see, only feel. And in some cases, this curvature guides matter not downward, but across, or inward, or around. We don't feel this on Earth. But the universe is not made for comfort. It is made of geometry, and geometry does not care what we perceive. There are even regions, cosmic voids, where the gravitational pull is outward. A kind of gravitational anti-well, where matter moves away, pulled toward surrounding walls of mass. In such regions, gravity feels like a repelling force, not because it pushes, but because there's less mass to pull you in. Imagine floating in such a place where the faint tug of gravity is not down or sideways, but away, from nothing toward everything. Even the shape of the universe may play tricks with gravity. If the cosmos is curved on a global scale, as some models suggest, then light and motion themselves follow paths that seem to wrap or bend in unexpected ways. Gravity in such a universe is not linear. It is topological, a maze, a fold. And one of the most haunting possibilities lies in gravitational waves, ripples in space-time itself, first detected in 2015. These waves, caused by titanic collisions of black holes or neutron stars, stretch and compress space as they pass. In their wake, gravity changes direction for a fleeting moment, not because the mass moved, but because space itself quivered. For that instant, up and down lose meaning. Gravity becomes a pulse, a whisper. In all of this, one thing becomes clear. Gravity is not what we thought it was. It is not a simple pull. It is a shape, a warping, a flow of geometry so deep and so subtle that our everyday lives barely hint at its complexity. On Earth, gravity keeps your feet on the ground, but out there, in the deep, curved corridors of the cosmos, gravity flows sideways, loops inward, twists, and wavers. It is as if the universe is breathing and gravity is the exhale. And in that breath, direction vanishes. So the next time you look up at the stars, remember, there is no up out there, no down, only mass, only motion, only the gentle undulations of a universe shaped by forces more ancient than time. And somewhere, far from here, gravity is pulling sideways. 8. You can't escape the universe. There's nowhere outside of it to go. We spend much of our lives thinking in terms of escape. We escape rooms, cities, routines. We dream of vacations, new lives, fresh beginnings. We imagine rockets rising from Earth, astronauts floating free, ships leaping through the dark. We think of space as the ultimate escape, a limitless frontier. But what if that, too, is an illusion? What if there is no outside? No edge to reach, no boundary to cross? What if the universe is all there is, and we are locked inside forever? This isn't a metaphor, it's a physical truth, a cosmic constraint written to the fabric of existence itself. When we speak of the universe, we mean everything. All of space, all of time, all of matter and energy, galaxies, stars, planets, radiation, fields, quantum foam, every observable thing. There is no beyond, there is no elsewhere. And perhaps most haunting of all, there is no way out. To understand why, let's start with the shape of the cosmos. For centuries, philosophers wondered if the universe was infinite. If you could fly in a straight line forever, would you eventually reach a wall? A curtain? An edge? Modern cosmology, grounded in Einstein's general relativity, offers a different picture, one far stranger and far more absolute. Space is not simply vast, it is curved. Not curved like a ball in three-dimensional space, but curved in the sense that it defines the space itself. Just as the surface of a sphere is two-dimensional but finite, the universe may be three-dimensional and finite, yet without an edge. If this sounds paradoxical, consider Earth. You can walk in one direction indefinitely and never fall off the planet. You'll eventually return to your starting point, not because Earth has walls, but because it's closed on itself. The universe may be similar. This idea is supported by data from the cosmic microwave background, the afterglow of the Big Bang, which suggests that space is flat or nearly flat, but possibly curved on extremely large scales. In such a universe, there are no boundaries, no places where space ends and something else begins, just more space and more time. But even if the universe were infinite, the result is the same. Infinity doesn't imply escape, it implies entrapment in vastness. Like a bird released in a fog with no horizon, you can fly forever and never leave. And yet we dream of exit. We imagine wormholes, tunnels through space-time that might connect distant regions or even other universes. We speculate about brains in higher dimensions, about quantum fluctuations that might punch holes in reality. But so far, all of these remain in the realm of theory, hopes, equations without evidence. Every attempt to define an outside hits the same wall. The universe isn't in something. It is everything. It doesn't expand into space. Space itself is what expands. The universe has no center and no outside. So where would you go? Even black holes, those cosmic maws of extreme gravity, don't lead outside the universe. At best, they take you inward toward singularities we do not understand. At worst, they tear information apart and leave nothing behind but event horizons and silence. Theories like the multiverse offer more tantalizing escapes. Infinite other universes, each with different laws of physics, branching realities like leaves on an eternal tree. But even if the multiverse is real, it doesn't offer you a way out. Because every universe, no matter how different, is still part of the same totality, and you are still inside. Consider this: even the speed of light, our cosmic speed limit, cannot take you beyond the boundaries of the observable universe. Light emitted from Earth today will never reach most of the universe because space is expanding faster than that light can travel. There are galaxies that are receding from us faster than light, not because they're moving through space quickly, but because space itself is stretching. Their light will never reach us. They are beyond our causal reach, as good as gone, and yet they are still part of the universe, still inside. You might wonder, if there's no outside, what lies beneath it all? What's the scaffolding? But there is no beneath. Space and time are not placed on anything. They are the stage. They are the structure. There is no deeper layer we can peel back, no hidden door in the basement of reality. This idea is deeply unsettling because it means you are not just trapped in your body or your mind or your culture. You are trapped in a cosmos that has no door, no escape hatch, no external point from which to see the whole. And yet, within that confinement, something miraculous has happened. You are here. You are not just part of the universe. You are a place where the universe looks back at itself. You are made of atoms forged in stars, stitched together by time and chance, given breath by entropy and evolution. And somehow, from within the prison of space, you ask questions. You search for meaning. You imagine freedom. That is not weakness. That is defiance. Because while you cannot escape the universe, you can explore it. You can listen to it. You can fall in love under stars and build instruments that capture light from galaxies billions of years away. You can hold the infinite in your thoughts. You may not get out, but you can go deeper in. And in that, there is beauty. So when you look up at the sky, know this: you are not beneath the stars. You are not outside them. You are within them, part of their story, part of their light. You cannot leave the universe, but maybe the universe has never left you. 9. The universe may already be dead, and we're just echoes of it. Close your eyes and try to feel the present moment. You are here, now, breathing, existing, thinking. But what if that moment has already passed? What if you're not living in the universe as it is, but in the slow fading glow of what it was? There is a haunting idea whispered among cosmologists and philosophers alike, that the universe may already be dead, that the great unfolding of existence is over, and what remains is merely the soft echo of a cosmic story that has already ended. It sounds strange, even impossible. How can we be alive in a dead universe? Is life, thought, and motion the very essence of something still living? But death, in cosmic terms, is not dramatic. It is not a final flash or collapse. It is quiet, slow, entropic. It is cooling, and it has already begun. To understand this, we must revisit what it means for the universe to be alive. Not in the biological sense, but in the thermodynamic one. In the early universe, seconds after the Big Bang, the cosmos was unimaginably hot and dense. Energy surged everywhere. Particles collided, recombined, radiated. Over time, matter formed. Atoms, stars, galaxies. The universe expanded, cooled, and organized itself into structure. Stars were born, burning hydrogen into helium, releasing energy that lit the darkness. Planets formed. Life, at least here, emerged. The cosmos was dynamic. It changed, it did things. But that period, the golden age of the universe, was a phase, a chapter. And it's already ending. The stars are dying. One by one, the brightest have already burned out. Blue giants lived fast and died young, exploding into supernovae. Yellow stars like our sun are halfway through their fuel. In the far future, only the dimmest, slowest burning red dwarfs will remain. Eventually, even they will go dark. When the last star flickers out, the stelliferous era, the age of stars, will end. The universe will grow colder, quieter. What follows is a long twilight. Black holes will dominate for a time, slowly evaporating through Hawking radiation. Galaxies will drift apart as the fabric of space continues to stretch. The night sky will fade to black. No new light, no new stars. And at some point, perhaps in 10 years, there will be nothing left that moves or burns. Just cold, lonely particles, thinly spread across a vast silent void. This is what physicists call the heat death of the universe, a state of maximum entropy where all usable energy has been dissipated. No more structure, no more activity, just equilibrium, a cosmic coma. But here's the twist, the truly eerie thought. What if we're already in it? Not at the end of time, but in the afterglow. You see, we don't observe the universe directly. We observe the past. Light from distant galaxies takes millions or billions of years to reach us. Even the moon's reflection is over a second old. When we look up at the stars, we are looking into a museum, a record, a projection. The most ancient light we can see, the cosmic microwave background, comes from a time just 380,000 years after the Big Bang. That light has been traveling ever since. But what if beyond that, nothing new is happening? What if the universe stopped changing eons ago? And what we call now is just the slow, graceful winding down of what once was. Entropy doesn't announce itself. It doesn't slam the door. It simply grows until nothing new can happen. No more complexity, no more surprise. And that idea that we are living in a fossilized universe, the echo chamber of a reality that has already run its course, isn't just poetic, it's mathematically plausible. There's even a term for it, the cosmic doomsday. In some models, the acceleration of the universe's expansion leads not just to heat death, but to an eventual breakdown of structure itself. Even atoms could be pulled apart in a big rip, a final unraveling of everything. But there's a softer version of that fate, where no rip comes, no explosion, no dramatic collapse, just stillness. In this view, we are like the faint ringing of a bell, long after it has been struck. The sound fades, but it persists, reverberating through the air until only silence remains. We are the reverberations of a universe that was. Your thoughts, your memories, your heartbeat. These may be the last complex patterns the cosmos will ever generate, the last shimmering waves in a sea that is slowly going still. This perspective changes things. It shifts the focus from grandeur to fragility. Because if the universe has already spent its creative energy, then everything we do, every conscious moment, every question, every act of kindness is part of the final bloom, the last breath of awareness before the long silence. And if that's true, we carry a kind of quiet responsibility to witness, to understand, to remember, even if no one is listening. There are echoes of this idea in religious and philosophical traditions. The notion that reality is not continuous, but decaying, that we are living not in the beginning, but at the end, that we are the dream of something already gone. But unlike dreams, the data persists. We measure background radiation, starlight, redshift, the dimming of galaxies, the thinning of hydrogen, and all of it points in one direction, outward, away, downward into entropy. The clock is still ticking, but perhaps not for much longer. Some find this terrifying, others liberating. Because if the universe is already dead or dying, then meaning is no longer something we wait for. It's something we create in the dark, in the cold, against the silence. We love, we wonder, we reach out across the void. And in doing so, we light a candle, however brief. So perhaps it does not matter whether the universe is alive or dead. Perhaps the only thing that matters is that you are still burning, still thinking, still dreaming. You are not the end, you are the echo. But echoes still sing, and that may be enough. 10. The universe is not made for you. It's barely compatible with life at all. There's a story we often tell ourselves, quietly, sometimes without realizing it, a comforting myth, that we are here because the universe was meant for us, that its laws are just right, that its stars shine to light our nights, that its planets turn so that life could flourish, that our existence is proof of a design. But the more we learn about the universe, the more fragile that story becomes. Because in truth, the universe is not made for us. It is barely compatible with us at all. Imagine floating away from Earth, past the clouds, beyond the pull of gravity, beyond the moon, beyond Mars. Soon you'll find yourself in the interplanetary void, a realm where sunlight fades into a whisper and temperatures plunge toward absolute zero. But that's still the friendly part. Keep going, past the edge of the solar system, beyond the heliopause. Now you are in true space. Out here, 99.99999% of the volume is a vacuum. Not just empty in the everyday sense, but empty in the absolute. A void so complete that a single atom might drift for miles before encountering another. A place so cold that heat becomes meaningless. A silence so deep that it becomes a kind of presence. This is the real universe. And it is inhospitable to life in every imaginable way. Let's start with the basics. Temperature. Life as we know it depends on a narrow thermal window. Too cold and molecules freeze. Too hot and they fall apart. On Earth, water exists in liquid form within a tight range, roughly 0 to 100 degrees Celsius. In most of the universe, temperatures hover just above absolute zero, around 2.7 Kelvin. That's minus 270 degrees Celsius. In space, your body would lose heat rapidly through radiation. Your blood would boil, not because it's hot, but because there's no pressure. Your tissues would expand. You wouldn't explode, but you'd be dead within minutes. Radiation. Without the protection of Earth's atmosphere and magnetic field, space becomes lethal. High-energy particles from the sun and distant galaxies pass through you, shredding DNA, altering cells. Astronauts in low Earth orbit absorb more radiation in a week than most people do in a year. Beyond Earth, protection is rare. Most planets lack magnetic fields. Most moons have no atmosphere. The sky may look beautiful from space, but it's deadly. Gravity. We evolved under a constant force, 9.8 meters per second squared. In microgravity, the human body weakens. Bones lose density, muscles waste, vision degrades. The cardiovascular system begins to fail. Long-term exposure is still not fully understood. Even gravity itself is capricious. On some exoplanets, it would crush you flat. On others, it would barely hold you down. And the physics that allows galaxies to form, gravity, dark matter, the expansion of space, comes from a delicate, unexplained balance of constants. If any of them were slightly different, stars would not form. Atoms would not bond. Time itself might behave differently. So why is it this way? Some have pointed to the so-called anthropic principle, the idea that we observe a universe compatible with life because we're here to observe it. If the universe were any other way, we wouldn't be here asking the question. But this is not a comforting answer. It offers no reason, only inevitability. Others invoke the fine-tuning problem. Certain fundamental constants, the strength of gravity, the charge of the electron, the cosmological constant, appear to be set within incredibly narrow ranges. If they were even slightly different, the universe would be either too chaotic or too inert for life to emerge. Some see this as evidence of design. Others suggest it means we are one of many universes, just the one where the dice landed in favor of complexity. But even in this rare pocket of compatibility, life is still clinging to the edges. Of the trillions of planets in the observable universe, only one is known to support life: Earth. And even here, life is fragile. One major impact, one supervolcano, one bad mutation, and evolution could have taken a different turn or ended. You were not guaranteed, and neither was consciousness. The human brain is a biochemical accident, a structure that evolved not for truth, but for survival. That you can sit here, now, and reflect on the universe at all is an extraordinary anomaly. Most matter in the universe will never think, never feel, never awaken. So when people say the universe seems fine-tuned for life, they are seeing only one part of the story. Yes, life can exist here, but only now, and only because 1,000 unlikely things happened in just the right order. And that makes you not a product of design, but a product of chance, a ripple in the sea of entropy. The truth is this: the universe is vast, and it does not care if you exist. The stars are not arranged to guide you. The galaxies are not aligned to teach you meaning. The laws of physics are not written with humanity in mind. They simply are. And yet, here you are, in this sliver of time, in this narrow band of temperature and pressure and gravity, breathing air that was once stardust. Built from atoms that were forged in suns that lived and died long before you were born. You are a local reversal of entropy, a brief bloom of order. You are life in a universe that doesn't need it. And that's what makes you profound. Because while the universe may not be made for you, you are made of it. And despite all odds, you've looked back at it and asked why. Perhaps the meaning does not lie in a universe that cares. Perhaps the meaning lies in you, caring anyway. 11. There's no guarantee the universe will follow the same laws tomorrow. We like to believe in order, in consistency. In a world that plays by rules, we trust that gravity will hold us to the ground, that atoms will behave, that the sun will rise again. We build our lives on this unspoken assumption that the laws of nature are not just true, but eternally true. But what if that's not the case? What if the rules themselves can change? What if tomorrow, without warning, the universe begins to behave differently? This unsettling possibility is not just philosophical musing. It is rooted in real scientific uncertainty. Because while the laws of physics appear stable, universal, and consistent across space and time, we cannot be sure they always were or always will be. And that means, in a very real sense, we are building our understanding of reality atop a platform that may not be fixed, but floating. Let's begin with what we think we know. The laws of physics are, as far as we can tell, the same everywhere. Light behaves the same in Australia as it does on Alpha Centauri. Gravity pulls with the same strength in distant galaxies as it does here. The speed of light, the charge of the electron, the mass of a proton, these constants seem truly constant, and yet we've only measured them in a very small corner of the cosmos and over a very short sliver of time. When we look at distant stars or galaxies billions of light years away, we are looking into the past. And from this, scientists can test whether the laws of physics have changed. Some studies, faint, subtle, controversial, have suggested that the fine structure constant, a number that characterizes how strongly particles interact with light, may have been slightly different in the distant past. If true, it would suggest that even the deepest constants of nature evolve. Imagine that. Imagine a universe where the laws of nature shift, not with whim or intention, but gradually, like a tide you can't see. Even tiny changes could ripple outward into chaos. If gravity were just a little stronger, stars would burn too fast. If the charge of the electron changed, atoms might not form at all. Chemistry would collapse. Time itself might behave differently. We are balanced on the edge of a knife, where the rules work just right to allow structure, energy, complexity, and life. But no law says they must stay that way. And here's the twist. Even if they did change, we might not notice right away. Why? Because we live inside the system. If the flow of time gradually slowed, or if the speed of light decreased in sync with all other interactions, we might never know. All of our instruments, all of our clocks, even our thoughts, would adapt in perfect lockstep. The rug could be pulled out from under reality and we would go on, unaware. This is the uniformity problem, a foundational assumption in physics that space and time behave consistently everywhere. It's a principle, not a proof. A lens we choose to look through. The universe does not come with guarantees. Physicist Paul Davies has argued that the laws of physics are not so much laws in the legal sense, but habits, patterns that the universe follows because it has always followed them. But habits can break, and if they do, we may not be prepared. Quantum mechanics itself hints at a reality in which probabilities, not certainties, govern the world. Particles don't follow strict paths, but exist in clouds of possibility. The universe may not be a machine, but a process, a dynamic interplay. Even cosmic inflation, the leading theory for the early moments of the universe, suggests that our laws of physics may be local, not universal. In other words, different regions of the multiverse, if it exists, could have different laws entirely. We live in a bubble where the rules are favorable. But that doesn't mean all bubbles are the same. If the laws of physics are not fixed but contingent, then our universe is not inevitable. It's an accident. And like all accidents, it may not last. There are theoretical scenarios too, frightening in their elegance. One is called vacuum decay. It proposes that what we consider the vacuum of space may not be the most stable possible state. Instead, the universe could be in a false vacuum, a temporary configuration that seems stable but isn't. At any moment, somewhere in the universe, a quantum fluctuation could cause a bubble of true vacuum to appear, where the laws of physics are different. That bubble would expand at the speed of light, rewriting the fabric of reality as it moved. There would be no warning, no defense, no survivors. The laws would simply change, and we would be gone. Even more haunting, the laws we rely on may be emergent, not fundamental. Some physicists believe that space-time, gravity, and even particles may arise from deeper, unknown principles, like patterns in an even more fundamental system, a kind of cosmic code beneath the code. If this is true, then the laws we know are not absolute. They are illusions, rising from complexity. Like ripples on water, they appear stable until something shifts the current. So what does this mean for you? It means that everything you take for granted, the ground beneath your feet, the breath in your lungs, the march of time, is conditional. And yet you live, you feel, you love, you build meaning in a world that may not be fixed. And that makes your existence even more precious. Because order in such a universe is not given, it is carved out. You are not standing in a world that is guaranteed to be kind or fair or consistent. You are standing in a moment of cosmic coherence, a brief window in which the rules work, the atoms bond, the stars shine, and your thoughts can exist. And that moment is a miracle, not because it was planned, but because it could have been otherwise. So sleep gently tonight, but know this: the universe owes you no stability. And yet, for now, it holds you anyway. 12. Most of the atoms in your body were born in stars that no longer exist. Take a breath, feel your chest rise, feel the air slip into your lungs, oxygen dancing into your bloodstream. That air, those atoms, were not made on Earth. They are older, far older. Now look at your hands, the calcium in your bones, the iron in your blood, the carbon in every cell of your body. All of it, every part of you, was once part of something else. Before there was you, there were stars. And before there were stars, there was only hydrogen and helium. Simple atoms born in the Big Bang. No planets, no life, no color, just heat and silence and potential. The early universe was, by our standards, incredibly dull. Without heavier elements, no carbon, no nitrogen, no oxygen, there could be no chemistry, no complexity, no you. That changed with time. When the first stars ignited, they began fusing lighter elements into heavier ones. In their cores, under unimaginable pressures, stars forged the elements that would one day become the seeds of life. Hydrogen into helium, helium into carbon, carbon into oxygen, nitrogen, silicon, and beyond. But even stars have limits. When they grow old, some swell into red giants, gently expelling their outer layers into space. Others, more massive, end in violence, collapsing and rebounding in supernova explosions, scattering their elements across space like a cosmic offering. These explosions don't just end stars, they create the conditions for new ones. And more than that, they leave behind the raw materials for life. Your body is not made from Earth, it is made from the ashes of stars. The iron in your blood was forged in the heart of a dying sun. The calcium in your bones came from a long-dead giant. The oxygen you breathe, birthed in the fusion core of ancient stellar furnaces. The poet Carl Sagan once said, "We are made of star stuff." And he was right. But what he didn't say, at least not in that moment, is that those stars are gone. Most of the stars that gave birth to your atoms have long since burned out. Some exploded before Earth even existed. Their light has faded. Their structures collapsed, their time ended. And yet, here you are, a temporary gathering of ancient dust, thinking about the stars that no longer shine. That's not just poetic, it's literal. The atoms in your body have existed for billions of years. They've passed through oceans, through plants, through the bodies of other animals. They've tumbled through volcanoes and glaciers. They've been split apart and rebuilt. But they began in stars. When you look at yourself, not in the mirror, but truly, you are not looking at something new. You are looking at something borrowed. Something inherited from a universe far older than your memory, your history, your species. You are a walking time capsule. And the atoms that form you, they're not done. One day, your body will return to the earth. It will break down. The carbon will be released into the atmosphere or buried in stone. The calcium will sink into the soil. The iron might become part of a mountain, or a seed, or the blood of something else. And perhaps, one day, those atoms will be pulled into the heart of a star once more. Because the cycle continues. Stars are born, they burn, they die. They scatter. New stars form from the remains. New planets, new possibilities. And maybe, on some distant world circling a sun not yet formed, life will emerge, and some part of that life will carry atoms that once lived in you. In this way, you are not just part of the cosmos, you are part of its ongoing story. A chapter, a sentence, a word. This cosmic perspective humbles. It reminds us that we are not separate from the universe, observing it from afar. We are the universe, a collection of atoms briefly arranged in a way that can think and feel and wonder. And yes, that arrangement is temporary. But the atoms, they go on. Some physicists believe that nothing is truly destroyed. Information, in some form, is always preserved. So while you, as you are now, will not last, the ingredients of your being will. They will flow through time, through worlds, through stars. You are a cosmic echo, and when your voice fades, it will become part of another. This realization is both deeply unsettling and deeply comforting. Because it means that death is not a boundary, it's a transformation. You are not falling out of the universe, you are falling deeper into it. And as you sleep tonight and your body finds rest, remember, the stars are not far, they are in you. You are their memory, and perhaps they are yours. 13. Entropy means you will never get this moment back again. Every moment that passes is unique, not because of what happens, but because of what cannot be undone. You breathe, a synapse fires, a leaf falls from a tree. Each of these things alters the state of the universe in a small but irreversible way. And the reason for this unidirectional flow of events, the reason why time appears to move forward and not backward, is something fundamental to physics. It is called entropy. In thermodynamics, entropy is a measure of the number of possible microscopic configurations that correspond to a system's macroscopic state. In simpler terms, it's a way of quantifying disorder, or more precisely, the number of ways energy can be arranged. And the second law of thermodynamics tells us something profound. In a closed system, entropy tends to increase. This means the universe as an isolated system is constantly evolving from lower entropy to higher entropy, from fewer possible configurations to more, from structured, useful energy to diffuse, unusable energy, from potential to equilibrium. Take a familiar example, a hot cup of tea cooling on a table. At first, the tea's molecules are more energetic than the surrounding air. But over time, the tea cools as energy flows into the environment, distributing itself more evenly. The overall entropy of the system increases. Heat doesn't spontaneously flow back into the tea. The process is irreversible. That irreversibility is what gives us the arrow of time. While the fundamental laws of physics, Newtonian mechanics, electromagnetism, even quantum mechanics, are time-symmetric, they work equally well whether time moves forward or backward. Entropy is not. It introduces an asymmetry, a direction. You don't see broken glass leaping back into one piece. You don't see smoke re-entering the fire. These processes are theoretically possible in reverse, but they are infinitely improbable due to the massive number of microscopic variables involved. And so time flows in the direction that entropy increases. This has enormous implications, not just for cups of tea or falling leaves, but for everything. Your memories exist only because time flows one way. Your biology, your metabolism, the very structure of thought and decay and learning are bound to the same principle. You age because entropy in your body increases. You digest food, grow, and move through chemical reactions that release energy and raise entropy in the environment. Even life itself, though it may seem like a force that resists disorder, does so only locally. Living organisms maintain internal structure by exporting entropy into their surroundings. Your body stays organized because you eat, metabolize, and release heat. In doing so, you increase the total entropy of the universe. Life does not defy the second law. It operates within it. And every heartbeat, every moment of clarity, every step through the world carries a thermodynamic cost. This is not bleak. It is simply the physics of reality. The current estimate of the universe's entropy is vast, but still not at its maximum. Stars still shine, matter still clumps. There are still gradients, differences in temperature, pressure, and energy that drive motion and change. But over time, these gradients will smooth out. Stars will burn their fuel, galaxies will scatter, black holes will evaporate. Eventually, the universe will approach a state of thermal equilibrium, where energy is so evenly distributed that no work can be done. This hypothetical state is sometimes called the heat death of the universe. Not because it is hot, but because all available energy has been used up. In such a universe, nothing changes. There is no time, not in any meaningful way, no structure, no thought, no contrast between one moment and the next. That final state lies unimaginably far in the future. But the journey toward it is happening now. Every physical process, no matter how small, nudges the universe in that direction. And that includes this moment. It includes you, sitting where you are, reading or listening or thinking. The arrangement of particles in your body, the pattern of light striking your eyes, the heat radiating from your skin, each is part of a specific configuration that will never occur again. Once this moment passes, its conditions will never return exactly. The entropy will have increased. You can recreate a setting, a memory, a photograph, but you cannot reassemble every atom. You cannot return every photon. You cannot reverse the diffusion of heat or the collapse of quantum states. Even the quantum world, governed by probabilistic rules, adheres to entropy on a large scale. The behavior of particles is uncertain, but the flow of information about a system, its correlations, interactions, and entanglements, still trends toward increasing complexity and irreversibility. In quantum thermodynamics, entropy can be viewed not just as disorder, but as a loss of information about the exact state of a system. And once that information is gone, it cannot be perfectly retrieved. This deepens the significance of entropy, because it's not just about broken eggs and warm tea. It's about the limits of knowledge. It tells us that even if you had perfect equations and infinite computing power, you could never fully reconstruct the past, not in its entirety. Entropy draws a line between what can be known and what can never be recovered. And that, perhaps, is why the present moment feels so fragile. Because it is. Physically, mathematically, permanently. Not in the dramatic sense of life or death, but in the quiet certainty that this arrangement of matter and energy, this configuration of neurons and temperature and thought, will dissolve into the next. There is no perfect repetition in the universe. And that makes now an incredibly special thing. Not because it is grand, but because it is unique. Entropy isn't a villain. It's not out to destroy. It's simply the natural outcome of probability in action. It gives time its flavor. It gives life its arc. It gives memories their weight, and it ensures that every moment you live is once only. So you don't need to hold on forever. You don't need to fight change, but you can notice. You can pause and say, this happened. And even as entropy carries the moment away, the fact that it occurred, that it was, becomes part of the universe's ongoing record, etched not in permanence, but in process. Because the universe doesn't rewind, it only unfolds. And that unfolding is happening now. 14. In a trillion years, all evidence that we ever lived may be gone. Human history is carved in monuments, etched into hard drives, preserved in DNA. We archive, we photograph, we write, we remember. And somewhere deep down, we hope that something, anything, will last. But time is patient, and the universe indifferent. No matter what we build, no matter how far we reach, there may come a time when all evidence of our existence vanishes completely. Not just the cities, or the languages, or the artifacts, but the signals, the molecules, even the atoms, everything, all gone. Let's begin with what we've already learned from Earth itself. Nature is remarkably good at erasing. Look at ancient ruins, stone structures swallowed by forest, pyramids covered by sand, entire cities buried by volcanic ash or ice. Within a few thousand years without human maintenance, buildings crumble, roads vanish, metals corrode, organic material breaks down. The Voyager spacecraft, carrying golden records etched with human knowledge, are currently speeding through interstellar space. But even these, though durable, are not immune. Bombarded by cosmic rays, pitted by micrometeorites, they will erode molecule by molecule over millions of years. And if they crash into something, their legacy ends instantly. Here on Earth, plate tectonics and erosion will eventually recycle the surface. In 100 million years, almost nothing of our current civilization will remain above ground. Even Mount Rushmore will smooth into a hill. The Great Wall will dissolve into dirt. Fossilization is rare. Data is ephemeral. Memory is fragile. But we imagine that in space, things last forever. That's not quite true. Even in the vast cold of the cosmos, time is corrosive. Over billions of years, stars like our sun will die. First swelling into red giants, then shedding their outer layers, leaving behind white dwarfs, dense, cooling embers. Heavier stars will explode as supernova, seeding the galaxy with heavier elements and collapsing into neutron stars or black holes. These stellar remnants, once considered eternal, are now known to be impermanent too. White dwarfs slowly radiate away their residual heat. After trillions of years, they will become black dwarfs, cold and inert. Neutron stars will do the same, and black holes will, through Hawking radiation, gradually evaporate over unimaginable timescales, up to 10 in years. That's a 1 followed by 100 zeros. Eventually, all luminous matter will fade, and with it, so will every trace of us. You might think, what about our signals? The radio waves we've been sending into space for over a century, they're out there, but they're spreading, fading. Every meter they travel, they lose strength, diluted by distance, scattered by cosmic dust, buried under the static of the universe. Eventually, those signals degrade below the level of detectability. Our messages, our music, our greetings, our stories will become indistinguishable from noise. And even if another intelligence heard them, they would not know who we were. They would not know what we meant. We think of atoms as eternal, but over time, even matter is not immune. Proton decay, a hypothetical process still unconfirmed, suggests that even the building blocks of matter might not be forever. Some grand unified theories in physics predict that protons may decay with a half-life on the order of 10^4 years or more. If this is true, then eventually, all atoms would fall apart. All molecules, all memory, nothing would remain. And even if protons are stable, the heat death of the universe awaits. 1 trillion years from now, the cosmos will be unrecognizable. The night sky will be dark. No new stars will form. Existing ones will be long gone. Galaxies will have drifted apart, pulled by the accelerating expansion of the universe. Eventually, most of them will vanish beyond our cosmic horizon, a boundary created by the speed of light and the stretching of space. From our point of view, they will become unobservable, effectively erased. This is not a collapse, it's a quiet dissolution. Everything we are, everything we've built, every triumph, every song, every struggle, it will all be forgotten. Not by society, not by culture, but by physics itself. Time is not just indifferent to memory, it undoes it. This idea is not meant to diminish what we are. It's meant to place it in context. We often speak of legacy, of leaving something behind, of being remembered. But the truth is, on a long enough timescale, nothing is remembered. Not because we were unworthy, but because the universe is unrecording. It doesn't store data indefinitely. It doesn't preserve voices. It doesn't keep score. Even the black holes, which we once thought might archive information in their event horizons, may ultimately lose it, either through evaporation or through processes we do not yet understand. And when the last particles of matter decay, when the last flickers of light go out, the universe will still exist, but it will be silent, still, and utterly blank. In that darkness, no one will remember us. No one will know we were here. No trace will remain. And yet, there is something strangely beautiful in this, because it means everything we do, everything matters only now, not in 1,000 years, not in 1 trillion, but now. Meaning is not preserved by the universe, it is generated by consciousness, by you, here in this moment. And when this moment passes, and it will, you carry it forward, if only briefly, into the next. And that is enough. So yes, in 1 trillion years, all evidence that we ever lived may be gone. But right now, you are here. And that is all the proof that ever mattered. 15. We might never know if the universe had a purpose, or none at all. When we look up at the stars, we instinctively wonder, why? Why are we here? Why does the universe exist? Is there a goal, a reason, a mind behind the motion of galaxies and the flicker of consciousness? This question has followed humanity across millennia. From the earliest myths to the frontiers of cosmology, we've searched for a purpose behind it all. A cosmic blueprint, an ultimate reason. But the deeper we look, the quieter the answer becomes. In fact, it may never come at all. Not because we aren't smart enough, not because we aren't curious, but because the universe itself may have no purpose to find. And if that's true, then we are explorers in a silent landscape, building meaning in a place that does not provide it. Let's start with physics. Our best models of the universe, from the standard model of particle physics to general relativity, do not contain intention. They describe what happens, how particles move, how forces interact, how time and space evolve, but they do not say why any of it should exist in the first place. The equations are elegant, predictive, powerful, but they are also indifferent. They don't suggest a goal, they suggest consistency. Some physicists and philosophers propose that the universe is what it is because it could not have been otherwise, that the laws of nature, the values of constants, the emergence of matter and structure all arose from deeper necessities. But others argue that the laws themselves may be contingent, random outcomes of a larger space of possibilities. This is where the idea of the multiverse comes in. In some models of cosmology, particularly those involving eternal inflation or string theory landscapes, there may exist a vast ensemble of universes, each with different physical parameters. Some are too chaotic to permit atoms. Others expand too fast for galaxies to form. Most never allow complexity at all. And ours just happens to be compatible with life. This is called the anthropic principle, not an answer, but a filter. We observe a universe with these properties because only such a universe can support observers like us. But this principle, while logically sound, is unsatisfying. It replaces why with why not. It leaves the deeper yearning unanswered. Is this all an accident? Could a universe really just pop into existence, uncaused from a quantum fluctuation? Some physicists, like Lawrence Krauss, argue yes. In certain models, the total energy of the universe might be zero, allowing it to emerge from a state of nothing that is itself unstable, a vacuum not truly empty, but seething with potential. But this nothing is not nothing in the philosophical sense. It still obeys laws, still holds structure. So we ask again, why those laws? And that question may never yield a definitive answer, because the universe may not be structured in a way that permits us to reach it. We are bound by our brains, our language, our logic. We are built to model patterns, not absolutes. Every theory we create is limited by what we can observe, test, and imagine. It may be that purpose, as we define it, is not a property of reality, but of minds. Biological minds, temporary minds. Your search for meaning is real, but the universe may not be designed to supply it. And that's the heart of this idea. We might never know if the universe has a purpose, because it might not have one. And if it does, it may be unreachable, a concept we do not yet and perhaps cannot ever comprehend. This isn't pessimism. It's the physics of epistemology, the study of what can be known and what lies beyond knowledge. Even in mathematics, there are limits. Gödel's incompleteness theorems prove that in any sufficiently complex system, there are truths that cannot be proven within that system. And we are part of the universe. We are inside the system, looking for the whole from within. That limitation is humbling, but it is also freeing, because it means we get to choose. If the universe has no assigned meaning, no imposed direction, then what remains is agency, yours. Purpose may not be given, but it can be generated. In biology, purpose is often emergent. Evolution doesn't operate with a plan, it selects for traits that confer survival. And yet life becomes more complex. Organisms evolve goals. Nervous systems generate intention. Minds reflect. Cultures shape narratives. So even if the universe is silent, you are not. You can choose to love, to create, to wonder, to observe the stars not for what they say, but for what they allow you to imagine. And that act of imagining, that may be purpose enough. Think about it. The atoms in your body came from stars. The rules that govern your cells were written by physics. Your thoughts are shaped by neural pathways evolved over billions of years, through entropy, through mutation, through chance. And yet, here you are, asking about the reason behind it all. You are the universe asking itself why. Even if there's no reply, the question itself is profound, because it implies consciousness, curiosity, a flicker of awareness in the great expanse. So will we ever know if the universe has a purpose? Maybe not. Maybe that question lies outside the realm of answers. Maybe it isn't meant to be answered, but maybe it's not supposed to be. Maybe it's meant to be lived. And in that living, perhaps the universe becomes just a little more aware of itself, a little more complete, even in silence, even without a reason. You've wandered far tonight, through dying stars, dissolving time, and the silent rules of a universe that may never speak. But though the cosmos is vast and perhaps indifferent, you were here. And you wondered. That alone is extraordinary. You are made of atoms forged in stars long gone, carried by entropy, bound by gravity, and yet capable of asking why. Perhaps there are no final answers. Perhaps the universe has no grand purpose. Or perhaps the purpose was always this: to become aware, to feel, to reflect. Let these thoughts drift with you now. Let them fade like starlight on still water. Sleep, not in fear of the void but in awe of it, because even if the universe forgets, for this quiet moment, you remembered it.